In this video, I want to talk to you about Dalton's law of partial pressures. So let's understand what that means. Let's say we have a vessel here off to the side and we have three different types of gases that are in that vessel. So we have red gas, green gas, blue gas. Now, what we could do to analyze this vessel is I could take my total number of moles that's in this vessel. I could take my R value and I could take my temperature, and then I can divide the total volume that's present in that vessel. And if I solve for that, I will end up getting the total pressure of this whole reaction vessel. Another thing that I could do to get the total pressure is to say, all right, well, I have these little pressures in here. So if I take the pressure of maybe the red plus the pressure of the blue plus the pressure of the green gas, and I add all of those together, then I could potentially get my total pressure also. So it's just a combination, the sum of all the pressures that I have built up in that vessel. That would be my total pressure. This first equation is just using the total information and my Pivnert equation to solve for my total pressure there. All it is PV equals an RT, and it's rearranged to solve for my total pressure. So that's what I can do to figure out the total pressure of this vessel. But what if I want to know just the pressure of that green gas? How do I figure that out? Well, if I have the moles of just the green gas, R, the temperature, and just the volume of the green gas, then I could, again, use my Pivnert equation in order to solve for the pressure of just the green gas. But what if I don't have all of that information? That leads us into Dalton's law of partial pressures. What a partial pressure is basically the pressure of the gas is a partial pressure. It's a small component of a total pressure system. The pressure of just the blue gas is a partial pressure of the blue gas. So it is just a small component of the total pressure that I have here. So in order to figure out my partial pressure, if I don't have the information to stick into Pivnert to solve for just that particular gas, what I'm going to use is this equation. The pressure of the gas desired is equal to the mole fraction of the gas. So this is mole fraction of the gas times the total pressure. So that's PT, my total pressure. Now there's something new here. Mole fraction. This is something we haven't learned before, I don't think. So in order to figure out mole fraction is basically what the name suggests. If I want to figure out the mole fraction of a particular gas, then I would figure out the moles of that gas desired and divide by the total number of moles. One thing to note, whenever you solve for mole fraction, you want it to be in decimal form. Do not change it to a percentage and do not leave it as a fraction. So for instance, if I want to figure out the mole fraction of the green gas here, I would figure out how many moles of the green gas that I have and divide by the total moles of all the gases that I have present in that vessel. And if I take that mole fraction of that gas desired times the total pressure, and again, I can figure out this total pressure by using Pivnert, or it could be something that's given to me. Then I can figure out the partial pressure of that particular gas that I'm trying to find. So now let's put this into practice. Let's work some example problems. So what this first one says is the partial pressure of oxygen was observed to be 156 torr, with a total, that's a key word there, total pressure of 743 torr. And we want to figure out what the mole fraction of O2 is. Now, when we work with these pressures, we always want to convert to ATM. So we are given a partial pressure. We are also given a total pressure, but those are in torr. So we want to convert to ATM first. So to do that, our conversion factor is 760 torr is equal to 1 ATM. So I'm going to take my 156 torr and I'm going to divide by 760 to get into ATM. I also want to do that for the 743. So 743 torr divide by 760 to get into ATM. And doing that math real quick, we end up getting 0.2 ATM. So 0.2 ATM for my partial pressure and 0.98 ATM for the other partial pressure. Now we're going to stick it into our equation. So the pressure of O2 is equal to the mole fraction of O2 times my total pressure. My 0.98 ATM is going to go in for total pressure. My 0.2 ATM is going to go in for my pressure of O2. And then I just have to simply divide to figure out my mole fraction. And that mole fraction ends up being 0.21. Now, notice how I leave it in decimal form. I don't try to change it to a percentage. I don't leave it in a fraction. And also, mole fraction does not have any units as well. So I'm going to clear the screen. We're going to go through the next example problem together. All right, for this next problem, what we are given is a mixture of helium and oxygen. And it says that we're going to put these into the scuba diving tank to prevent the bends. For the particular dive, we have 46 liters of helium at 25 degrees Celsius and 1 ATM. We have 12 liters of O2 at 25 degrees Celsius and 1 ATM, and they're pumped into a scuba tank with a volume of 5 liters. So we want to figure out two different things, or actually more than two different things. We want to figure out the partial pressure of each gas, and we also want to figure out the total pressure in the tank. So here's what we have to do first. This information that they gave us about helium was before we put it into that tank. So we need to figure out how many moles that is. If we know how many moles that's in this, the helium that's going to be put in the tank, and we can also figure out how many moles of O2 that's going to be able to be put in the tank, then we can put those together to figure out the mole fraction of each. And if we know the mole fraction of each, we can start looking at figuring out a total pressure. And if we can figure out a total pressure, then we'll be able to figure out the partial pressures as well. So this is our approach. We're going to first use this information in order to solve for moles of each of my partial gases. Then we're going to figure out mole fraction. We're also at probably the same time, we're going to figure out the total pressure, and we can use that with PivNert, and then we can solve for the individual partial pressures. So a lot of stuff going on here. So let's start with finding out moles of the helium. So if I use PV equals nRT, and I plug in all of the information given. So my pressure is 1. My volume is what I'm solving for. I'm sorry, your volume is not what you're solving for. Idiot move. Your volume is given to you at 46 liters. My bad. So 46 is what you put in here. Moles is what we're solving for. Our R value we know is 0.0821. And our temperature is 25 degrees Celsius, but we have to use the Kelvin form, so that's 298. So the moles that you get, and this is for helium, ends up being 1.88 moles of helium. All right, so 1.88 moles. Now I'm going to do the same exact thing for my oxygen. I'm going to use PivNert, PV equals nRT. And I'm going to solve for the moles of my oxygen. So pressure is 1, volume is 12, N is what I'm solving for, R is 0.0821, which I'm just going to leave it as R, and temperature, again, is 298 Kelvin. So when I solve for my moles of oxygen, O2, I end up getting 0.49 moles. Now that I have the moles of both of my species, I can figure out the mole fraction of helium, and I can also figure out the mole fraction of O2. To do that, I'm going to take the moles of helium, so 1.88, and divide by my total moles. Now, my total moles is just going to be the sum of both of those, which ends up being 2.37. So when I solve for my mole fraction of helium, I end up getting 0.79. That's 0.79 right there. I do the same thing to figure out my mole fraction of O2. So I'm going to take its moles, which is 0.49, divide by the total moles, which is 2.37, and that value ends up being 0.21. Now that I have the mole fraction of each, I'm going to have to figure out my total pressure. So my total pressure, I'm going to solve from PivNerd by taking my total moles times R times T and dividing by my total volume. So the volume is going to be 5 liters because that's what volume we're going to have when we pump both of those gases in. So total moles is 2.37. R is your R value. Temperature, it says 25 degrees Celsius, so that's 298, over volume, which is 5 liters. So my total pressure ends up being something around 11.6, 11.7 ATM. So I've answered one of these questions. My total pressure, check. I've got it done. Now to figure out the partial pressures, I'm going to take the mole fraction of helium times the total pressure, and that will give me my pressure of just helium. So pressure of helium is equal to mole fraction, which is 0.79, times total pressure, 11.6, and that ends up being 9.2 ATM. Now, to solve for my other partial pressure, I could actually do two different things. One thing that I could do is take my mole fraction times my total pressure, or what should both of these pressures equal to be? Well, if I add both of these pressures, those should be 11.6. So I could potentially say 11.6 minus 9.2, or I could take the mole fraction, 0.21. This is kind of maybe like a check and balance system if you want to use it. So 0.21 times 11.6 is equal to 2.4 ATM. Now, if you want to check yourself, you say, all right, well, 9.2 plus 2.4, what does that equal? Well, that's equal to 11.6, which makes sense because both of these pressures added together should equal my total pressure that I have in the system. So this is dealing with Dalton's law of partial pressure. It's just a little bit of PivNerd and mole fraction and figuring out where to plug in all of this information. So I hope this is helpful, and I will see you later.